Okay, so this is a review of the coursework question 1, 1A and 1B, covering part 1 of the mechanics course. And so, question 1A is a question about polar coordinates. And the question reads, as a ladder of a fire engine is extending at a constant rate of 200 millimeters a second and is simultaneously being rotated at a constant rate of 3 degrees a second. Determine the magnitudes of velocity and acceleration of the fireman at point A for the position shown in figure A. Now, a couple of people asked about clarification for this question, whether the rotation was in the plane of the paper, so i.e. if the rotation was in this way, or if it was out of the plane of the paper, and the intention was that it was in the plane of the paper. I think everybody submitted answers to that effect. So, the first thing to do, and something that a couple of people didn't do, you draw your diagram, you define your theta, you define your r, and you define your axes. It's really important to find your unit directions and to state that you're going to be using polar coordinates. So the next thing to do is to summarize the information that you've been given, and that's what's included here. So you have to read between the lines and work out that the total radius is 6 plus 3. You have to convert degrees per second to radians per second. And then you're expected to make a statement of interpreting the question, since it's being extended at a constant rate and rotated at a constant rate, and you know that both theta double dot and r double dot are 0. You need to make a statement to that effect. If you just put that they were 0, you would have lost a mark. Then it's just a case of using the definitions for polar coordinates. For VR is equal to r dot. That's a simple one. V theta is r theta dot. Remember always to compute your answer with the units. And then once you've got both the components, remember that this is the component in each direction of the polar coordinates. The magnitude is going to be the Pythagoras. So the question asks for the magnitude, so you have to take the square root of the sum of the square of the two components, and this is the answer. For the velocity. For the acceleration, it's exactly the same principle, but you have to make use of the definitions for AR and A theta, which again you wouldn't need to memorize. They'd be provided to you in an exam. Since these are 0, the first term is 0 in both cases, then it's a case of substituting in the values above, taking the Pythagoras again, and again finding the mean. A couple of things to point out. Try to be consistent in the number of decimal places that you report. Try to always use your units, and try to give some comments as to the direction your answer is taking. In question 1b, you're asked to consider the situation where you have a mass B sliding down a rod, hitting a spring, compressing the spring and coming to a stop. And you're asked to work out in 2 stages. First of all, the velocity when B reaches this first point, which you can call C, and then finally in part 2, at what point does the spring, or what point does it come to a stop? What's the maximum deflection of the spring? So there's another point D beyond C. And there's two ways you can solve this. Fairly similar to start with, but subtly different in the way in which they're applied. So the first of which is work energy, and in this case you're saying that the kinetic energy at point B plus the work done between B and C is equal to kinetic energy at point C. So TB, work done, B to C, is equal to TC. It's initially at rest, so first off you can say that the kinetic energy at the beginning is 0. Then it's a case of working out which forces are acting, what work is done. And remember, for the work that's done, you have to consider only the forces in the direction of the motion. So looking at the forces in the direction of the motion, you have friction, of course, which is opposing the motion, and you have a component of the weight, which is responsible for the overall motion down the rod, and you just have to equate those two forces. So you have the work done being equal to the positive work done by the weight minus the negative work done by the friction, times by the distance. So that's the distance over which they act, so it's the distance between B and C. Now, in order to find the friction, you have to go back a step and you have to work out what is the reaction force. And the reaction force R is going to be equal to the components. Show that. R is going to be equal to the component in the normal direction of the weight, so it's going to be mg cos theta. Once you've found R, you can find friction, and you can work out that the work done between B and C is just under 0.2 times the weight. This is equated to the final kinetic energy, which includes the unknown Vc, which is what you're looking to solve to begin with. If you equate all of them, then you can manipulate these expressions to get the answer, 1.93 meters a second. Okay, and the other way you could solve this is simply force acceleration. And this is possible in this case because we're assuming that the acceleration is constant, so the gravity is constant over the duration of the motion. And if you look at the two expressions, you equate both fx and fy. Fy should be 0 because there's no motion in the y direction, whereas fx, there is motion, it's in the ax direction. You put a subscript x there. And if you equate the forces in the x direction, you have the weight down the slope minus the friction. It must be responsible for your constant acceleration. So you get your acceleration is equal to the weight minus the friction. And using your Suvat equations, your v squared is equal to u squared plus 2as, you can then get the answer. And this seems more simple. It's perhaps a less general approach because it's assuming that, well, it's only possible here because the acceleration is constant. And of course, either approach is fine. Okay, then finally for the part 1b2, you have now the colour has reached point C and now it's working against the spring between C and D. So the point here is that you've travelled from B to C, you've hit the spring with a speed Vc, and now you're slowly going to do work against the spring until you come to a point where you come to a stop. And this is an energy balance between C and D, and you start with a kinetic energy, Tc, you finish with no kinetic energy, Td, which is what's first outlined here. And in between those two states you have three forces acting. You have the weight, the friction, don't forget the friction is still on the rod, and you have the spring. Now quite a lot of people, when they did this question, forgot about the work done by the friction and by the weight, and if you just consider the work done by the spring, then that's responsible for most of the work done, but you get a reasonable approximation of the answer, but you wouldn't have got full marks because these two contributions are not negligible. So Td is 0, you're left with Tc, which is using a value you already have, 7.45 joules, and work done between C and D. So it's just a matter of defining these three contributions. So the work done from the weight is the component of the weight in the direction of the motion times the direction over which the spring compresses, xd. The friction again times xd times the friction force, but this time it's negative. And the work done by the spring, in this case, the force is changing as a function of the compression, so you have to integrate. You integrate between a zero compression and xd, the final compression of the spring, and it's always a negative force, a negative work done, because it's against, the force is acting against the motion of the collar. So you integrate this, you have kx squared over 2, and again it's negative. You put in the limits, it's xd squared minus 0 times k over 2, all minus. The total is minus 900 xd squared. And with these three terms then, combined with the kinetic energy at c, Tc, you get a quadratic as a function of xd, and you can solve that directly to get something very close but not quite equal to 10 centimeters, and that's the answer. Other ways of solving this, you could have done the analysis directly between points B and C, and considering and D, the final state, considering the length 0.5, and then the additional distance xd. Some people did that, and that's fine. If you refer to the coursework feedback sheet and the sheet with these solutions and additional comments, then there's extra information there. Okay, that's it.